All right. As a senior propulsion architect, my job is to solve the hardest problems in flight. And today, we're going to pull back the curtain on the two components that are really the secret sauce to unlocking long-range, commercially viable eVTOL flight. So let's just get right to it. Following a top-down approach, I'm giving you the answer first. The key here isn't just one component, but this deep symbiotic relationship between a digital brain, the motor controller, and a mechanical heart, which is a very, very special clutch. Now, before we get into the nuts and bolts of our solution, we first have to really define the fundamental problem it's designed to solve. This is the why that drives every single engineering decision we make. Look, current battery technology with energy densities around 200 to 250 watt-hours per kilogram, it's great for short city hops, what we call urban air mobility. But for longer flights, it creates this severe battery bottleneck. Think of it this way. With today's batteries, an eVTOL might fly you from Manhattan to JFK, no problem. But it could never take you from New York to Boston. That's the barrier we have to break. So how do we break this bottleneck? Well, the answer isn't just a bigger battery. It's a smarter, much more elegant architecture. Let's take a look at the P13 series parallel hybrid solution. It's really a masterclass in engineering efficiency. Okay. This schematic might look a little complex at first glance, but the core idea is absolutely brilliant. You can see right here how the P13 system combines the best of both worlds, series and parallel hybrid systems. This gives us the quiet, zero-emission flexibility of a series hybrid for takeoff, and then the incredible efficiency of a parallel hybrid for cruise. And the physical switch that makes all of this possible is one critical component, that K0 clutch. This system is smart. It dynamically selects the most efficient power path. So in series mode, you get about 85% powertrain efficiency. But by closing that clutch and switching into direct drive mode for cruise, we can push that efficiency up to an incredible 95 to 98%. Now, that 10–13% gain might not sound like a lot, but in aviation, that's the difference between a profitable route and a money-losing one. It's a total game changer. So now that we understand the overall architecture, let's zoom in on the system's intelligence, its central nervous system, the motor controller unit, or MCU. The MCU is really the unsung hero of this whole system. It's not just some power switch, it's a digital conductor. It orchestrates the flow of energy with the precision of a brain surgeon, all while actively protecting the entire mechanical system from itself. A key design choice, and it really underpins our efficiency-first philosophy, is the 800-volt high-voltage architecture. It's a simple principle, really. By doubling the voltage compared to older 400-volt systems, we actually cut the current in half to deliver the same amount of power. And less current means less energy wasted as heat, which allows us to use lighter wiring. And that is a huge win in aviation where every gram counts. This high-voltage strategy is all made possible by using advanced silicon carbide, or SiC, power electronics. You can think of these as the Formula One cars of the semiconductor world. They switch power on and off at incredibly high speeds with almost no energy loss, allowing us to hit that peak inverter efficiency of over 98.5%. That tiny percentage gain translates directly into more miles of range. And this is where the MCU's intelligence really shines. It basically acts like a set of noise-canceling headphones for the entire powertrain. You see, the combustion engine creates these harsh vibrations. The MCU senses them and injects a perfectly timed opposite vibration to cancel them out, which protects the clutch and the drivetrain from literally being shaken to pieces. Okay, now for the mechanical heart. This is the component that physically arbitrates the flow of power. It's what translates the MCU's digital commands into mechanical reality. This one question, it drives the entire design philosophy of the clutch. It's a question we absolutely have to answer with 100% certainty. What happens if the engine seizes up in midair? So, the crucial point is this. The clutch is designed to be power to lock, and this is a non-negotiable, mandatory safety requirement. It means if control power is ever lost, internal springs literally force the clutch open. This physically guarantees that a seized engine can never, ever lock up the propeller, ensuring the aircraft can always fly to a safe landing on electric power. This isn't just some nice-to-have feature. It is the bedrock of our safety philosophy. It's our ultimate lifeline. Now, to perform this safety-critical role, it has to be incredibly fast. We require it to engage in under 200 milliseconds for a smooth transition, but in an emergency, it has to disengage in under 100 milliseconds. Just to put that into perspective, a blink of an eye takes about 300 milliseconds. This clutch can isolate a failed engine in less than a third of that time. Speed is safety here. A brilliant design is completely meaningless without proof. In aerospace, we don't assume, we verify. So this is how we forge an aviation-grade system. The entire system is put through an absolute gauntlet of tests. We start on what we call the copper-bird rig, where we're injecting electrical faults to test every single safety logic. Then we move to the Iron Bird, which is a full-scale ground test rig where we run thousands and thousands of flight cycles. And finally, we subject the components to extreme environmental torture testing according to DO 160G, the international standard for airborne equipment. Now, the software and the hardware controlling the thrust are, by definition, flight critical. What that means is if they fail, the consequences could be catastrophic. Because of that, they must meet the highest safety standard in all of aviation, Design Assurance Level A, or DAL A. Meeting the DAL A standard means we have to quantitatively prove that the probability of a catastrophic failure is less than 1 in a billion flight hours. To put that into perspective, a single aircraft would have to fly continuously for over 114,000 years to reach 1 billion flight hours. That is the almost unimaginable standard of safety that we engineer to. So it all comes back to that concept we started with. The success of this system hinges on the fusion of intelligent control from the MCU and robust, fail-safe mechanics from the K0 clutch. It's this perfect marriage of digital intelligence and mechanical integrity that makes the whole P13 system so revolutionary. This synergetic design is what solves that battery bottleneck we talked about, not with brute force, but with an intelligent, safe, and hyper-efficient architecture. This is what makes clean, quiet, regional air travel a commercial reality. And that leaves us with a final thought to carry forward. We've seen how this deep integration of intelligence and fail-safe mechanics has unlocked the future of aviation. So the question I'll leave you with is, where else in our world could this same approach fundamentally change what we believe is possible?